So I thought, oh, I'll take the time and I'll get the network working.
So I noticed there's still people coming in, but I think we have to start at some point. Welcome everyone to the second plenary session of EvoStar, and I have the honor to welcome Professor Alan Bundy from the School of Informatics of the University of Edinburgh. Now, if you have the honor to introduce a plenary speaker, you have to do, if you want to do it properly, you have to do some background research, which is much easier nowadays with the internet. So I did my background research, and I have to admit that this actually turned out to be quite a sobering experience. Because like any young researcher, I really would like to find out how to be successful and how to get people to use my ideas and to read my papers. And of course, a young researcher then hopes that you can learn by actually following good example. Now we know Alan Bundy is a good example because this year, for example, he joined the elite ranks of the few honored by the ICHGAI, and he was given the Research Excellence Award. For example, Marvin Minsky also got this award years ago, very prestigious award. But why the sobering experience then? Well, I think I found out from the bare statistics that success comes from actually very hard labor. To date, Alan has written 5 books, published around 170 papers, held almost 50 research grants, and I think most incredible, delivered over 40 PhD students, and that's within 36 years. So that means that he's delivered at least one every year. What's the secret behind this success? Well, I was quite lucky because I had the fortunate opportunity to observe Alan's group for a while, and I think it's Alan's ability to create a very serene environment for his team to work in, and this enabled them to publish in collectively more than 300 papers. But at the same time, he also is able to stimulate them with the many visitors and the regular seminars that he hosts at the Edinburgh University. Now, Alan is also very generous, and he spreads his way of doing science by returning the favor, having done more than 75 research visits in his career and giving numerous invited lectures, as he's about to do for us now. So Alan, if I can get you up to the stage. Can I please have a...
Well, thank you very much, Jano. Is this on? Everybody here? Okay. I hope I can live up to that billing. I didn't quite recognize that person there. My talk is Procuring and Patching Proof Plans. So my research is on automated reasoning, almost nothing to do with evolutionary computing, I'm afraid. I was surprised to be invited to this conference, but Jano explained to me that you always invited somebody from way off field. But I spotted a little bit because, as you'll see, I've been just toying a little tiny bit with evolutionary computing ideas just recently. So most of my work is on proof search, guiding the search for proof in mathematics and as applied to formal methods of verification, synthesis, and transformation of computer programs and hardware. I'm also interested in the ways that new representations are discovered and formed and then evolve over time to deal with new kinds of situations. And we've looked at many other aspects of representation and reasoning, including finding counterexamples, dealing with uncertain reasoning, the presentation of arguments, and so on. And we've looked at applications in mathematics and formal methods mainly, but also in other areas like games. I did for a while some work on computer bridge, and we did some work on Go and so on, and also configuration of computer programs and things like this. So one of the main themes of this work is what I now call proof planning. So you have to understand that just as with evolutionary computing, one of the main problems in automated reasoning is control of search. So it's relatively easy to represent a mathematical problem as a set of axioms and rules to be manipulated, and this defines a huge search space which then has to be guided. And one of my main contributions is to look at ways of thinking about that space at a higher level. So the idea of a proof plan is that you have, first of all, your object level domain of interest, which could be reasoning about numbers or lists or tree structures or, as I mentioned, bridge hands. But then you have a meta level of inference, a higher level of inference, the domain of which is the formulae at the lower level, at the object level, and the proof methods that are available to you, and the heuristics that are available to you there. So you can start reasoning about reasoning about what is the kind of problem that you've got here, what are the proof methods which are available for its solution, how can we choose amongst them, how can we put them together in a sensible way. And in this way we build a plan first, a high-level plan of the overall proof, and then gradually flesh it out. And this inference at the meta level, deciding what kind of problem you've got, how can you go about solving it, then helps guide the inference at the object level. And the reasoning essentially is analyzing your current goal and then deciding, forming a plan of how you're going to go about proving it. So what are these proof plans? Well, they start from the point of something called tactics, which were invented by Robin Milner way back in the 70s. Tactics are computer programs which guide the search for a proof by applying rules of inference from your logic. And in fact, the original language for writing these tactics, which Milner invented, was the ML, functional programming language, and the ML stands for meta level. So this enables you to usually work backwards from goals, conjectures you're trying to prove, to sub-goals via some rule of inference. And then you can combine these hierarchically. So you can have some very low-level ones which just do some simple things, and then you can start putting them together with others into a larger tactic, and so on, hierarchically, building them with recursive functions in a language like ML. Now, our addition to this is what we call methods, and the methods specify the behavior of these tactics. So they say, under what preconditions are these applicable, and is it sensible to apply them, and what kind of effects do they have? And then by using AI-type plan formation, you can then put these methods together. You can say that the effect of this one will enable the preconditions of this other one, and therefore they can be put together into a little mini-plan to solve this piece of the proof. And in that way, you can build up a whole plan for the proof. But these plans don't always work. There's always a level of optimism in the abstraction at the meta level, and so in practice they can fail. But when they fail, an analysis of what it was you were trying to do from the meta level perspective, from your proof plan perspective, and the exact nature of the failure that occurred can help suggest a patch, and I'll give you an example of that later. So we have this notion of critics, which analyze the failures of the plans and then suggest a patch. And in this way, we can successfully guide search, and we can also explain how some of these heuristics work, why it is that this is a successful method of search, because it enables this other thing, and it follows from this other thing, and so on, and fits together into this overall plan. So here's a sort of graphical depiction of a particular plan that we've been developing for some while, which we call the induction strategy. So this is for proofs by mathematical induction, not the learning type of induction. in which you just see lots of examples of something and generalize from them. But mathematical induction, where, for instance, on the natural numbers, you prove something first for 0, and then assuming it's true for n, prove it for n plus 1, and so on. So the prove it for 0 is called the base case. The application of the rule is called induction, and the assume it for n and prove it for n plus 1 is called the step case, so that's represented by this box here. There may in practice be more than one base case and more than one step case. And then inside, this is how we've gone about doing the step case of the proof. There's a process called rippling, which I'll explain in a minute, and then followed by something called fertilization. So we've broken down these steps and seen that this kind of pattern occurs an awful lot of the time and can be exploited to control this kind of proof. And the inductive proofs are amongst the hardest to control, so this is a particularly challenging example to apply this technique to. I put down here what is the precondition of this strategy. There are many, many forms of induction, and declaratively this says that the form of induction you choose enables this rippling process to do its stuff. And procedurally, you can interpret it as, well, choose a form of induction which will enable this rippling to work. Here's a particular proof plan for what is deceptively simple theorem, the commutativity of addition. Here's the overall proof plan on the right here, which consists of 3 applications of this induction strategy. One to the original theorem, x plus y equals y plus x, and then that generates 2 subgoals, y equals y plus 0 from the base case, and this from the step case, and that requires another application of induction on y each time. And what I've shown here is that you can take one of these and zoom in, blow this up. This is like the structure that we had on the last slide. So you can zoom around. These graphical representations of the plans we call HiProofs. They're a kind of high graph. I don't know if you've come across high graphs. So high graphs are graphs in which the nodes are high graphs. And so this is a particular application of that to give us a visual tool for exploring the structure of what could be quite a large proof. Okay, so I mentioned this rippling a few times. Let me just say what that is. So here's a simple example of rippling on a very simple theorem called the associativity of append. So this symbol here is going to be an infix form of list append. And this symbol here with the double colon is the infix form of list constructor, the cons operation in Lisp. And so this says it doesn't matter in which order you append 3 lists. I can append y and z together and then append t on the front, or I can apply t and y together, append t and y together and then append z on the back, and I'll get the same result. So this is just like associativity of many other binary operations in algebra. And this is the inductive proof. It's an induction on this variable here, t. This here is actually the induction hypothesis, the sort of n case that you assume, and this is the n plus 1 case that you then have to prove. So this is the step case of the induction. And you'll see that there are these yellow boxes and things in red, and let me explain that. So the idea is that typically in an inductive proof, the hypothesis, the given, is actually syntactically quite similar to the induction conclusion or the goal to be proved. The bits that are the same are in red, and the bits that are different are in black with orange boxes or yellow boxes around them. And the idea of rippling is to enable you to use the given to prove the goal by moving these orange boxes, yellow boxes. I call them orange because they're orange on my scheme, but they're yellow up here, sorry, so I'll try to remember to call them yellow boxes. Is to move them out the way. So you'll see that these, as you go down these steps of the proof here, these 4 steps, the yellow boxes get bigger and have bigger holes containing more of the given. And eventually, they contain a copy of the whole of the given. And at this stage, we can say, well, this is true, so that whole expression there is true, and simplify the whole thing down to h equals h and true, which is trivial to prove. So that's the idea, moving these boxes out of the way, making them grow bigger, and the thing that you use to do this is called wave rules. So this is called rippling because you're meant to have this mental image of standing beside a loch in Scotland where it's apparently warmer there than it is here today, and there's the reflections of the mountains in the loch, and somebody throws a stone in, and the ripples spread. So the reflection is disrupted, but it's only temporary. The ripples grow bigger and bigger, and eventually the whole mountains are reflected once more in the loch. So that's what's happening here. These are the ripples on the pond, as it were. And you can see here particularly how they get bigger and bigger until they eventually swallow up the whole of the given again, and the reflection is restored. And it's done with the aid of these rules. So this rule comes from the recursive definition of append. It says to append this h cons onto t to L, you first append t to L recursively, and then you append, and then you cons h onto the front. And this, you see this structure of moving the wavefront, the yellow box, out. And so repeated applications of these, in fact, that very rule will give you this moving out effect. Let me give you another illustration if this works. So, come on. Why is it taking so long? I had it all set up. Well, there was going to be a demo at this stage but somehow the web page seems to have died. Never mind, we'll go on. So what are the advantages of this? Well, it's a selective form of rewriting, because when you rewrite like this, you insist that the yellow boxes in the rewrite rules, the rules that you're applying, match up exactly with the yellow boxes in the goal. And this cuts down the amount of possible rewrites that you could do, quite dramatically, in fact. So on the whole, there's only one thing that you can do, so there's very little search when you apply this. It's not exhaustive. It's not sort of just throwing every possible rule at the expression that might apply. It's matching them up with these yellow boxes. And it's also guaranteed to terminate, so the skeleton is the sort of red bits that stay the same, and the measure can be read off from these yellow boxes moving in a desirable direction. So one can attach a well-founded measure to that and show that they terminate. So here, it doesn't matter which set of rules that you have, as long as they have these properties of being skeleton preserving and measure decreasing, you can be sure that they will always terminate. And this is even true if you use a rule in both directions. So you can take a rule and you can use it in either direction, but of course the annotations will be different. So, that's why it didn't work. Okay, my connection must have gone down. Why am I not surprised? You can actually see it, I think, in this rule. So you could annotate this rule in a different way. You could annotate it by making h const onto t be the skeleton and the append L be the wavefront. And then it would go in that direction. It would move in the other direction. So this rule can be used in both directions, but with different annotations. And it's the different annotations that prevent it from looping, even though it's being used in the same direction. So this is quite a nice feature, because there are some proofs in which the same rule can be used in both directions. And normally that's a complete no-no in automated reasoning, because it can cause loops which you don't want. So normally it's forbidden, but this actually allows it, which is interesting, and allows it in a way that still terminates. So in a minute you'll see that it also can be a heuristic basis for doing all sorts of clever stuff. So choosing intermediate lemmas, choosing generalizations, case splits, inductions, and so on. So I said inductive proofs was nasty. One of the ways it's nasty is it has all sorts of infinite branching points within the search. And so choosing an induction rule is an infinite branching point. Deciding to introduce some intermediate lemma is an infinite branching point, because there's no way of predicting which lemma it might be. It's, in general, it could be anything. Generalizing the formula, again, is an infinite branching point. So these are often called eureka steps, because they seem to require human intervention, and most of the inductive reasoning in automated theorem proving is done interactively with a human in the loop to decide, on these steps what should be done. So, but we found ways of automating that using essentially the breakdown of rippling to inform a patch, the effect of which is to do one of these clever things, and I'll illustrate that in a minute. Okay, so it's been empirically quite successful. We've implemented it in a variety of what we call proof planners. This Lambda clam, and is a planner. Well, I won't bore you with the details, but these were systems that we built ourselves. Omega was built by a group in Saarbrücken. It's been applied on a wide range of domains. So here's some of the areas, not just in induction. And rippling, actually, which was invented for induction, actually turns out to apply all over the place. So we've seen applications in analysis, in summing series, in transfinite ordinals, all over the place. So that turned out to be quite surprising. It's a very common pattern, it turns out, a very common kind of proof plan in mathematical reasoning. And we've even applied this proof planning idea, as I said, outside of mathematics in computer configuration and bridge. Okay, so just to summarize that, so these meta-level annotations that you see in these orange boxes enable you to prune the object-level search space and also to measure your progress by some termination measure. The meta-variables act as a kind of, so I haven't explained about meta-variables, but I will explain in a minute. So we can use variables which stand for unknown structure as a kind of least commitment device for postponing important search decisions, like which induction rule you should use and how one should synthesize things. And then the object-level inference is then performed and provides us with the goals which we then analyze at the meta-level and manipulate. Okay, so my next phase is to explain about these critics. So this is the patching part of the talk, how we can patch these failed proof plans. So when a proof plan fails, that failure can be exploited productively. We can analyze the form of the failure and suggest an appropriate patch depending on the form of the failure. And so these critics, which are based on failures of rippling, can suggest things like a change of induction rule, an intermediate lemma, a generalization of the theorem, or a case split. I just got time to illustrate one. I'm going to illustrate the intermediate lemma one because it's really the simplest. So we call this lemma speculation because it first speculates and then proves a missing lemma. So this is another simple example. So the associativity of associativity of pen, which I showed you before, is the kind of E. coli of inductive theorem proving. It's a very common example that people illustrate their ideas on. And this one is a sort of fruit fly of inductive reasoning. This is another very common one. This is an example. So the idea here is that rev reverses a list. So obviously, if you take a list and reverse it, and then reverse it again, you'll get back to the original list, which is what that says. So it's sort of intuitively obvious. Take a list, reverse it again, you're back where you started. But surprisingly difficult to prove by induction. So actually, there's a lot of examples like this of things which appear to be obviously true, but quite tricky to prove by induction. And so this is an example where a straightforward version of rippling can break down, depending on which wave rules you've got. So I'm assuming that the only rule we've got is this one from the recursive definition of reverse, which says to reverse a list of the form h const onto t, first reverse t recursively, and then append the singleton h onto the back of the list. So this is a very naive form of reverse, very inefficient version, but so it just simply illustrates the problem. So typically, if you just started reasoning about reverse, this will be all you've got, just the definition of reverse, and this might be one of the first theorems you think to prove because it seems sort of obviously true. But if you see how you apply it, so here's the given again, here's the goal, the step case, the induction conclusion, where we've replaced the L here with h const onto t. Well, that should have been a t, never mind. We can apply this rule here to this expression, and it results in this here, okay? And now we're stuck. Nothing applies to this. There are no rules which apply to this, okay? So this is blocked. What we would like to do now is move this yellow box through the reverse to reveal the whole of that, the whole left-hand side of this expression in this